It was a day that sort of changed things. The university president even came over to see me that day. I had no idea we were such good friends. The telephone voicemail was jam-packed with requests for interviews, and then I came through the voicemail to a familiar voice of one of my colleagues from Norway. And I'll never forget his voice. He said, Peter, we've just heard the news. It's unbelievable. And the voice came back on and said, no, it's very believable, and it's wonderful. Nice to have the confidence of your colleagues. Well, let me thank you for being present in my lecture. And let me thank my hosts for inviting me to be here. It's a pleasure to be here. And let me just restate what I've said before. I think Thailand is a young country with a brilliant future. And the young people, those of you sitting here, are really the future of science. Don't give up. It's probably the most fun career you could possibly pursue. Thank you. The relative amount of water transported by the co-transporters is much smaller than with the aquaporims. So that water transport might be very important, particularly in the gastrointestinal tract. But as far as massive movements of water, it's a relatively smaller amount. So I think the studies you described are probably going to be very important. Macular degeneration, retinal tears, loss of vision are a horrible problem. And maybe some of these studies will provide new insights that could result in the prevention of vision loss. Wouldn't that be important? Thank you for your question. Yeah, yes, sir.
You mentioned about the transport of glycerol through the aqueous glyceroporim, and I was wondering, has the work been done on the transport of other alcohol such as methanol and ethanol? Can they pass through this aquaporim like protein?
So the question, can alcohols permeate aquaporims? We looked carefully at the problem of methanol transport, methanol being structurally closer to water than any other chemical. And the problem with alcohol studies is that the baseline permeation through the lipid bilayer is very high. So the diffusion pathway for methyl alcohol is enormous. And we can't see an incremental increase in oocyte studies, for example, where we add methyl alcohol or add aquaporin RNA. So we simply can't do the measurement. My sense is, in fact, alcohols freely permeate aquaporins. We just can't make the measurement. Now, polyol transport is a different thing. Of course, glycerol is a polyol. Ethylene glycol. The baseline permeation of these molecules is much lower and can be boosted enormously by the presence of the aquaglyceroporins, up to 4 carbons, I guess. And after that, things stop. So I think your thinking is right on, that the baseline permeation prevents us from making a measurement. Thank you. Other questions? Yes, behind you.
So I'd like to ask for APQ1. I'd like to ask for APQ1. Okay. And then one of your slides you mentioned for the proton, for the prevention of the proton contact. And you say one of the barriers is site restriction and then electrostatic repulsion. So my question is that have you confirmed for the site directed messages? Change that histidine and arginine to something else and then see the effect?
A very knowledgeable question. Are the specific residues in the narrow part of the channel each essential for the repulsion of protons? And some studies have been done site-directed mutagenesis, not in all homologs, but in AQP1, we're unable to replace the asparaginase by anything else and get a functional molecule. Now, we failed to be able to do this. It may be that other combinations of mutations can be done, My sense is this is such an important part of the molecule, and the folding is so tight that the expression of most mutants will be unsuccessful. The folding will prevent their normal trafficking into the membrane. So I suspect that these molecules, these residues are essential, but I can't prove it by mutagenesis. Now, maybe you have information. Have you, in your studies, tried this?
I just asked for the histidine 180
Yeah, the
and
histidine,
the
yeah.
arginine, the
Sure.
one that you
Right.
for the side restriction and then electrostatic repulsion. The first barrier,
Yeah,
not
so
the second barrier. The first barrier.
So the first
So you
barrier
have-
is an arginine and a
An arginine and histidine.
Yeah. So I'm thinking back into the gloomy recesses of my brain for studies we've done some years ago, and I'm not coming up with the answer. The arginine is essential, and with very few exceptions, arginines are present in all homologs. If I recall correctly, some of the plant tonoplast membranes, now these are intracellular membranes, where pH gradients are not known to occur. Some of these membranes may lack that arginine. And physiologically, the importance of the plasma membrane of the plant cell, of course, is critical, since the proton ATPase is the electrochemical gradient maker. But I don't have more insight than that.
My second question is probably rather crazy. Compared to
Crazy
the
questions are the good ones.
APQ1 and the APQ9 or the Aquaporim. So I did wonder again for the selectivity. Would it be possible to change those residue and then change the selectivity? Is there anyone done that?
Yeah, there has been suggestion that a couple of these residues could be changed so that an aquaporin could be an aquaglyceroporin or the reverse. There's a group in France that reported this in homologs from insects, but when we attempted to do this with bacterial and human proteins, we couldn't express them. So, in addition, these proteins are not identical. Orthologs between species are virtually identical. Aquaporin 1 from human tissues and from rat tissues are more than 90% identical. But aquaporins 1 and 2 are only about 30% identical, and aquaporins 1 and 9 are probably about 20% identical. So some functional residues are perfectly conserved and others aren't. So that's close enough for intelligent exchange. But now that we have the structures, some of these studies could be done. And I encourage people to jump in on these aquaporins and do the studies. My lab is a small lab. We're only going to pick a few areas to work on. And I think it's important that others work on this. Because even though big labs are moving in, you feel like, well, they've answered the questions, mistakes occur. And I would have to say that I regret that our field has had more than its share of mistakes in the literature. And I think this is a very clear-sighted question that should be answered. I hope you or others will do that. I'm too old. Is there time for another question? Yes, please.
I'm Dong Hwan from biochemistry. I would like to know about the regulation or control of this channel. You mentioned one thing that the phosphorylation lead to trafficking of the channel to the membrane. Are there other regulations like switch off, open, or close of the channel?
Thank you. So, excellent question. Regulation. Is there a gating mechanism to aquaporins? I think the most advanced information is coming from the plant investigators. In particular, Per Schaldholm and his colleagues from Lund, Sweden, have made some very interesting observations. Some information is unpublished. I can't in a public setting reveal it because it would be privileged. But I think they have very clear evidence that in plant plasma membrane aquaporins, that gating does occur. Phosphorylation of specific residues. And these residues don't appear to be important in mammalian channel gating, but in plants, it appears to be a good way of regulating their open and shut probability. Now, one of the problems with measuring gating is water is electrically silent. Expression of water channels cannot be measured by patch clamp analysis to measure rapid flickering of ion channels. The one homologue that does contain ion conduction properties is Aquaporim 6. I have not presented that this afternoon because it's a little complicated, but it has a large anion formation, and this is work of Masato Yasui, who's presently at Johns Hopkins. He's a Japanese national investigator. And it looks like Aquaporim 6 has a rapid flickering, but as far as we know, there's no phosphorylation dependent. It's a pH induced gating event with specific residues playing an important role. So I think your question is right on the mark, and I think more work needs to be done. Thank you. Over on the far side, please.
I really enjoy your talk. And actually, my question just have same as what Ajahn Dongkwon just asked you. But what I would like to relate is about the APP5 to the straight brand. Think about the regulation of the estrogen and the correlation, because in the menopausal woman, they will have a nice sweating, and usually with the aging, you should have a decline or the down-regulation of the expression of the aquaporin, but in this case, it seems like you have the up-regulation.
Sure. So, fine question. I think there are age-dependent expression differences in aquaporins. I think that's quite clear. I believe the known concentration defect after age 50, I find I can't sleep through the night. I have to get up in the middle of the night to empty my bladder. It's probably an underexpression of aquaporin too. Now, the question related to perimenopausal sweats, the hot flashes. As far as I know, the biology has not been worked out in terms of aquaporin participation. But in terms of the gland functions, of course, they're involved. There's no question that aquaporin 5 is involved. But it is likely that the physiological basis, of course, is an adrenergic phenomenon, where the triggering and the control mechanisms are too tightly wired in some way. And so it may be that aquaporins are important components of this, but as far as I know, it's not yet established. But this is an important question. As I become middle-aged, my sisters, my wife, the wives of my friends, they're all in this age group where these processes are really quite important. The importance of bone reabsorption, the form of osteoporosis, is of course of tremendous clinical consequences, because millions of women around the world at the perimenopausal stage of life start to develop increased bone reabsorption, which can lead to fractures and severe disability. And that is a problem that we're intensely curious about, because aquaporin 9, which is a glycerol transporter, is present in the osteoclasts. And that may play a role in the bone reabsorption of the menopausal situation. I don't have other information. Thank you. Yes, right underneath there. Hi. Could you see the lecture actually from down there?
Just wonder that the aquaporin is alpha helix transmembrane domain that form the pore. That's my knowledge. Or the porin is the viral structure.
So the porin, P-O-R-I-N, bacterial porins, which are outer membrane channels of beta virials. Aquaporins are unrelated to bacterial porins, just as albumin is unrelated to ovalbumin. They sound the same. The structures of the aquaporins are largely alpha helix, but the pore itself contains alpha helix and random coil, so-called random. It's not totally random, of course. So the actual pore itself is part alpha helix, but beta structures are not present in any significant amount in aquaporins. Thank you for making that important distinction. Are we running out of questions?
Somewhat an older person to ask. Oh, you talk about the role of ADH.
You're not older unless you're older than me.
Stick to the question.
61.
Well, you talk about the role of ADH in terms of the activating insertion of the A2P2, I think, only two collecting atoms. What about the expression, the up-regulation and down-regulation? Does ADH have a role in controlling the amount of A2P2 in the cells?
Thank you for asking that. In my discussion of Aquaporim 2, I kind of mentioned the trafficking from the intracellular side to the surface, and then I talked about some clinical states where they're overexpressed and underexpressed. But chronic thirsting of animals, normal humans, leads to increased capacity to absorb urine. And this is known to lead to overexpression of the Aquaporim 2 protein. So, in fact, this chronic thirsting does alter the expression of the protein. Probably water, the compulsive water drinker, individuals who are known not to be able to concentrate the urine, even when you take the water away, at least acutely, are probably underexpressing the protein. So those are examples of where expression levels change. Now, I think in terms of other aquaporins, the expression levels are probably where we can deliver some pharmacological benefit. Right now, when an expectant mother undergoes premature labor, 7th month labor, for example, early 3rd trimester labor, they can pharmacologically slow down or stop labor in many cases, but not in all cases. When it's clear that they can't stop the premature labor, these women are injected with glucocorticoids because it's known that the unborn, the premature infant, once born, has a lot of very serious handicaps, one being lung function, other being vulnerability to central nervous system hemorrhage. And some of these consequences are in part ameliorated by empirical glucocorticoid treatment. Now, work of Landon King, I showed you a picture of Dr. King. In fact, he's in the back row on the left there, who's a lung specialist, has shown that, in fact, expression of Aquaporim 1 in lung is exquisitely sensitive to the presence of glucocorticoids. So that's another situation where glucocorticoids can lead to increased expression. So as an asthmatic takes a glucocorticoid inhaler, presumably that's one of the benefits. So thank you, that's a very good question. And all members of the audience are welcome to ask questions. Yes, please, young lady.
Talking about Aquaporim 4 in the mice that have the brain damage. I wonder that can we relocalize Aquaporim 4 to be like the normal mice, so reduce the brain damage in the normal mice?
Excellent question. Is it possible to reduce expression of Aquaporim 4 in brain or induce it? Now, I gave you kind of the first analysis. Aquaporim 4 is important in the fluid movement into brain substance during the appearance of brain edema. But Aquaporim 4 is also the mechanism for the movement of fluid out of brain substance. So if we inhibit Aquaporim 4 at the exact time of brain injury, we could theoretically at least diminish the chance of brain edema. But once the edema has been occurring, if we inhibit the Aquaporim 4, then it's problematic because we can't move the fluid back out of the brain. So it's, again, an experimental approach to genetic therapies, but in fact will be a very tricky type of procedure because aquaporins don't distinguish between water going one direction or the other. If the gradient is pointed in this way, the water goes this way. If the gradient is the other direction, it goes the other direction. Glycerol is a little different. The glycerol can be captured within cells by glycerol kinases. You can phosphorylate glycerol. So you can bring glycerol across membranes against the glycerol gradient by phosphorylation, but water we can't do that. So, in fact, you brought out an important point. There are going to be some problems with Aquaporim 4 inhibition. One thing I didn't touch on in the lecture, I guess you haven't told me I can't talk more. If Aquaporim 4 is deleterious in the setting of brain edema, why do we have the protein at all? And this is turning out to be a very interesting subject. A number of investigators are looking at this. Our colleagues in Norway, Dr. Otterson, Mahmoud Amiri, Arlen Nagel, as well as Jeff Manley and his group in California. And what they're finding is that the aquaporin 4 is needed for the fluid movement to move potassium during potassium siphoning. So neural activation, potassium is leaving neurons. It's then taken up by astroglial cells. But it's taken up as part of a fluid, potassium along with water. So the potassium channels move potassium out of the parenchyma into the astroglial cells, and the aquaporins move water. And in the aquaporin 4 null, or excuse me, we haven't looked at those, we don't have access to those mice. But in the mistargeted aquaporin 4 mice, they do better with regard to brain edema, but when they have epileptic seizures, the seizures are more severe. And this vulnerability to seizures, I think, is the reason the protein is present. And that's being looked at by others. Even a recent human study, which we just published, collaboration with workers at Yale and in Norway, our Norwegian colleagues, have found that in mesial temporal lobe epilepsy of humans, the sclerosis of the CA1 region of the hippocampus coincides with an underexpression and a mislocalization of aquaporin 4. Thank you.
Any other questions?
Well, those are very good questions. You know, that's the problem. They get up in front and the smart people are down there. They're the ones that have the good questions.
If not, there's a couple of things that I need to inform before Professor Yotthai coming up to the official closing. Professor Yotthai, of course, is the president of Thai Academy of Science and Technology. I have to read because it's a long name. Not Yotthai is a short name, but his institution is a very long name. I think our audience must agree with me that Professor Peter Agre lecture is both believable as well as wonderful. I think he has shown us a lot, and we have learned a lot. Actually, I was thinking throughout this lecture, separating 28K and 32K is not difficult. Thermosine blue as well as Silverstein also not difficult. Is it? No. Expression in your OSI is not. So perhaps winning Nobel Prize is not difficult. We do enjoy the lecture very much. Thank you very much. We would like to request Professor Sikano to present a token of our appreciation. Professor Sikano is a member of University Councils as well as the former board of Thailand Research Fund. Perhaps over there.
It's a photo op.
Professor Peter Agre will be with us until 4:30, sitting in the next room here in 102, and it's open for everyone. So after coffee, please, and want to talk with him either on aquaporins or cross-country skiing or camping, please come to him. Don't leave yet, Professor Yotthai, please.
On behalf of the Faculty of Science, Medieval University, the Thailand Research Fund, and the Thai Academy of Science and Technology, I would like all of you to join me to thank Professor Agre for his wonderful lecture. Thank you very much.